Welcome back to our Mineralogy and Geology lecture series. In our last video, we defined what mineralogy and geology are, traced their history, and saw how they connect through the rock cycle. Today, we go deeper. Because geology and mineralogy are not just one thing, they are entire families of sciences, each with its own focus, tools, and real-world impact. By the end of this video, you will know the major branches of both mineralogy and geology, what each one studies, and why each one matters. Let us get started. Think of earth science as a great tree. The trunk splits into two major limbs, mineralogy and geology. Each limb then branches into specialized subfields. Scientists working in any one of these branches contribute to our collective understanding of the earth. Some work underground. Some work in laboratories. Some work with satellites. All of them are reading the same planetary story, just from different chapters. Let us begin with mineralogy. Mineralogy is not a single discipline. It is a broad science with several interconnected branches. The oldest and most foundational is descriptive mineralogy, also called systematic mineralogy. This branch focuses on identifying, describing, and classifying minerals based on their physical and chemical properties. Things like color, hardness, crystal form, cleavage, luster, and specific gravity. It is the branch that gives every mineral its name, its formula, and its place in the classification system. If you want to know what a mineral is, descriptive mineralogy is where you start. The second major branch is crystallography, the science of crystal structure. Every true mineral has a crystalline structure, meaning its atoms are arranged in a precise, repeating, three-dimensional pattern. Crystallographers study these atomic arrangements using techniques like X-ray diffraction. This tells us not just what elements are present, but how they are bonded and arranged, which determines a mineral's hardness, cleavage, optical properties, and much more. Without crystallography, we could not design the semiconductors in your phone, the alloys in aircraft engines, or the pharmaceutical crystals used in modern medicine. Next is chemical mineralogy, also called mineralogical chemistry, which examines the chemical composition of minerals and how elements combine to form them. This branch uses tools like electron microprobe analysis and mass spectrometry to determine the exact elemental makeup of a mineral sample, sometimes down to parts per million. Chemical mineralogy is essential in ore deposit studies. Knowing the exact chemistry of a mineral tells us how to extract valuable metals from it and how to manage toxic byproducts safely. Optical mineralogy, sometimes called crystal optics, studies how minerals interact with light. When polarized light passes through a mineral thin section under a petrographic microscope, each mineral produces a unique pattern of colors and interference figures. These optical properties, like refractive index, birefringence, and extinction angle, allow geologists to identify minerals with remarkable precision, even in tiny fragments. Optical mineralogy is fundamental to the analysis of rocks in thin section, which is one of the core skills you will develop in this course. Finally, there is economic mineralogy, the study of minerals that have commercial, industrial, or strategic value. Economic mineralogists assess where valuable minerals are found, in what concentrations, and how they can be sustainably extracted. This branch sits at the intersection of science, engineering, economics, and environmental management. From the gold in South Africa, to the lithium in the Atacama Desert of Chile, to the copper in the Democratic Republic of Congo, economic mineralogy underpins the global resource economy. It is one of the most career-relevant branches for students pursuing work in mining, exploration, or environmental consulting. Now let us turn to geology. If mineralogy is focused on the building blocks, the minerals, geology is focused on the structure, the history, and the dynamic processes of the entire planet. And geology is an enormous discipline. In this section, we will walk through its most important branches, from the classical to the cutting edge. Petrology is the study of rocks, their origin, composition, structure, and classification. Petrologists examine all three rock types: igneous rocks that crystallize from magma, sedimentary rocks formed from deposited material, and metamorphic rocks transformed by heat and pressure. Petrology is closely linked to mineralogy. you cannot understand a rock without understanding its minerals. In the field, petrologists use hand specimens and field maps. In the laboratory, they use petrographic microscopes, geochemical analysis, and geochronology to date and interpret rocks. Structural geology and tectonics studies the architecture of the Earth's crust, how rocks are deformed, folded, faulted, and displaced by the enormous forces inside the Earth. Structural geologists map faults, folds, joints, and fractures to understand how the crust has moved and deformed over time. This knowledge is critical for earthquake hazard assessment, for understanding oil and gas traps, and for predicting where mineral deposits may be concentrated. In Kenya, for example, the East African Rift System is one of the most tectonically active regions on Earth, making structural geology highly relevant to local students and practitioners. Geophysics applies the principles of physics to study the Earth's interior. Geophysicists use seismic waves, gravitational measurements, magnetic fields, and electrical resistivity to probe structures deep below the surface that no drill could ever reach. When an earthquake occurs, the seismic waves it generates travel through the Earth and are recorded by instruments worldwide. By analyzing how these waves bend and reflect, geophysicists have mapped the Earth's core, mantle, and crustal boundaries. Geophysics is also the backbone of oil and mineral exploration, using methods like seismic reflection surveys and gravity mapping to locate buried resources. Hydrogeology is the study of water in the geological environment, specifically groundwater, its occurrence, movement, and interaction with geological materials. Groundwater is stored in permeable rock formations called aquifers. Hydrogeologists assess where aquifers are located, how fast water moves through them, and whether they are being contaminated by natural or human-made pollutants. In many parts of the world, including large parts of sub-Saharan Africa, groundwater is the primary source of drinking water for communities not connected to municipal supply systems. Hydrology is therefore one of the most socially impactful branches of geology. Environmental geology examines how geological processes and materials affect human beings and ecosystem. Environmental geologists assess natural hazards like landslides, earthquakes, and volcanic eruptions. They also evaluate the environmental impacts of mining, construction, and waste disposal. As climate change accelerates, environmental geologists are increasingly called upon to assess coastal erosion, permafrost thaw, and sea level rise. This is perhaps the most interdisciplinary branch of geology, linking directly to ecology, public health, engineering, and policy. Mining-affected communities in particular rely heavily on environmental geological assessments. Paleontology is the study of ancient life through fossils. While it overlaps strongly with biology, paleontology is firmly rooted in geology. Fossils are found in sedimentary rock, and their distribution in rock strata tells us about Earth's biological and environmental history. Paleontologists use fossils as index fossils to date rock layers, reconstruct past environments, and understand major events like mass extinctions. Understanding where and why life changed on Earth is inseparable from understanding the geological conditions that drove those changes: sea level, climate, volcanic activity, and more. One of the most important things to understand is that these branches do not work in isolation. They are deeply interconnected. When a mining company wants to open a new copper mine, they need economic mineralogy to identify and value the deposit, structural geology to understand fault systems that might affect underground safety, hydrogeology to manage groundwater, environmental geology to assess ecological impacts, and petrology to characterize the host rock. A geothermal energy project requires crystallography to understand the minerals precipitating in pipes, geophysics to map the underground heat reservoir, and hydrogeology to manage the fluid flow. In your career, you will very rarely work in just one branch. The most effective geoscientists are those who can think across multiple disciplines simultaneously. Today, we explored the rich family of subfields within mineralogy and geology. In mineralogy, we covered descriptive mineralogy, crystallography, chemical mineralogy, optical mineralogy, and economic mineralogy. In geology, we explored petrology, structural geology, and tectonics. geophysics, hydrogeology, environmental geology, and paleontology. Each branch has its own methods, tools, and applications, yet all are connected by the shared goal of understanding the Earth and managing its resources wisely. In Topic 3, we will begin exploring one of geology's greatest concepts, the geological timescale and plate tectonics.